Yes. Hello friends. Today we will go for another important derivation, that is the separation of variables in Laplace equation in spherical polar coordinates. So let me read the title: separation of variables in Laplace equation of spherical polar coordinate. As we all know, spherical polar coordinate has three parameters or coordinates or variable, that is r, theta and phi. So the Laplace equation del square psi can be written as del square psi of r, theta and phi. Before that, we must know how to write Laplace equation in the spherical polar coordinate system. That is already we have discussed in few for earlier discussions. So this del square is given by dava square upon dava r square plus 2 upon r into dava upon dava r. This is an operator, or everything is an operator, plus 1 upon r square sine theta into dava by dava theta multiplied by of sine theta into dava upon dava theta. This is the third term, and plus last term is 1 upon r square sine square theta into dava square upon dava phi square. So this is my Laplacian or Laplacian operator in case of the spherical polar coordinate system, and therefore Laplace equation becomes here. So write this del square in the earlier equation. We will get dava square psi upon dava r square plus 2 upon r dava psi upon dava r plus 1 upon r square sine theta into dava theta of sine theta into dava psi upon dava theta, and last term is plus 1 upon r square sine square theta into dava square psi upon dava phi square is equal to 0. Call this to be equation 1. We have to deal everything now with this equation as follows. So as usual, we are writing here. So let's assume this particular step in the separation of variables. Let's assume this psi of r theta phi, the solution which we are supposed to get here after solving this equation, is a product of three functions: r, which is function of r alone, then capital S is function of theta alone, and capital T, which is function of phi only. So there is no relation between small r and capital S, small r and capital T, or theta and capital R, phi and capital R. So all these are independent functions of each other. So using this in our equation 1, now I am writing this in short as a product r, s, t, and we have to understand this is function of r, s is function of theta, and t is function of phi only, exclusively, as always we understand. So here now first term can be written as dava square r s t divided by dava r square plus 2 upon r dava r s t and divided by again dava r, plus next term is 1 upon r square sine theta into dava by dava theta of sine theta into dava r s t, again this psi can be replaced by r s t, upon dava theta plus 1 upon r square sine square theta into dava square r s t upon dava phi square is equal to 0. Now look at this equation. In this equation 2, or the next this equation, here out of this product r s t, only r is function of this small r. Here similarly in the case number 3 or term number 3, Here this deva rst upon deva theta, so here is s is function of theta only, so r and t can be taken out of this term. Similarly, in this last term rst, t is the function of phi, so rs can be taken outside. So we can write next as is, this is s into t, that is out of this. So deva square, now this deva square can be replaced by d square because r is function of small r only. So d square r upon dr square. Similarly, second is again here it is s into t multiplied by 2 upon r into dr upon small dr. Again here is a differential, not partial differential written to be there. Then here r and t that can be taken outside, which are not functions of theta, so it is rt upon r square sine theta into, this is now d by d theta of sine theta into ds upon d theta. That is my third term in the equation, which will get converted like this. And finally here r and s will be taken outside because this is not function of phi, so r square into sine square theta, this gives me d square t upon d phi square is equal to 0. Now this equation is to be divided by psi again, psi is equal to rst. So dividing above equation by psi is equal to rst throughout. So let's divide it by, all terms are to be divided by rst. So in the first case st gets cancelled, so what remains is 1 upon r times d square r upon dr square plus st again gets cancelled, 1 upon r times, this is 2 upon r into dr upon small dr plus again rt gets cancelled here, so it is 1 upon capital S into r square sine theta multiplied by d theta of sine theta into ds upon d theta. That is my second term. And finally last term also, here r and s will get cancelled, so 1 upon capital T into r square sine square theta, okay, this, and then finally we get this is multiplied by d square capital T upon d phi square is equal to 0. Now one more thing we have to do here. If I look that equation, above equation, here r square appears here in the third term and fourth term. So to cancel this r square from here as well as here, if I multiply the entire equation by r square, then let's see what happens here. So this first term on the left hand side becomes, this is small r square upon capital R d square r upon small dr square plus one of this r will get cancelled here, so it is small r upon capital R, 2 can be written here, into dr upon r plus, now this is 1 upon capital S into sine theta, r square will get cancelled, into d by d theta of sine theta into ds upon d theta. And similarly in the last term this r square will get cancelled, and therefore it is 1 upon t into sine square theta multiplied by d square capital T upon d phi square is equal to 0. Now look at this equation. Here this equation can be seen. Now term 1 and term 2, these are exclusively depends upon small r. So there is no theta dependence here, there is no phi dependence here. Here is the theta and phi dependence. See, this is again theta dependent. Here is theta and phi dependence. So we can separate out these two terms from the remaining terms here. So I can write, therefore this is r square upon capital R into d square r upon small dr square plus 2 small r upon capital R into dr upon small dr is equal to minus, all the terms are to be written on the right hand side, so 1 upon S sine theta into d by d theta of sine theta into ds upon d theta, this is my first term here, plus 1 upon t sine square theta into d square capital T upon d phi square, this bracket. Call this to be equation number 2. Now this equation shows you. Okay, so see what is our equation number 1. This is what our Laplace equation in this case. Now doing all these arrangements or rearrangements, we get this equation is equation number 2. Now this equation suggests left hand side of this equation is this, exclusively dependent upon r. Right hand side is depends upon theta and phi. So this mathematically it is true. That means this equation can be true only when left hand side and right hand side are numerically equal to some constant. As I said earlier, now to choose this constant is what requires the knowledge of the problem, that what type of symmetry that your problem is for which you are solving this particular differential equation, as well as what type of constant we choose. That as I said, mathematician's choice may be different, but physicist's choice may be different. Here we are taking physicist's choice to bring all these equations, whatever resolved equation or the separated variables, these differential equations, they should have some standard form. In that sense, we have to go for such type of selections of the constant. So here let's write in brief the RHS, okay, LHS, the above equation can be true only both LHS and RHS are equal to independently equal to some numerical constant. And now let's see what type of constant we choose here. Say some lambda. I don't know what this value of lambda, but there is some numerical value associated with that, and therefore this equation 2 can be written. We will get two separate equations from this equation 2 as follows. So let's see. Left hand side gives you, this is r square upon capital R into d square capital R divided by dr square plus 2r upon capital R into dr upon small dr is equal to lambda. Again, write this second side will write somewhat later on. Now take this r here and divide this entire equation by r square. So what will happen here? So I'll get here or multiply this each and every term by capital R upon r square. If I do that and rearrange this equation, so this will give you d square r upon small dr square plus this r again goes here, and this one of this r can be cancelled, so it becomes 2 upon r into dr upon small dr, and minus lambda, I can take this lambda here, so it is to be multiplied by capital R upon r square is equal to 0. So I can write, I have written this equation as d square r upon dr square plus 2 upon r times dr upon small dr minus lambda upon r square into this capital R is equal to 0. This is my equation number 3. This is actually r part equation. So we have separated one variable here, and I got this standard differential equation as given by this. So this is called as r part equation. Okay, first 1/3 of that is we have calculated. Now let's go to the next, that is this right hand side. Now right hand side can be equated to again lambda with this negative sign here. So I can write next is equating. Now from equation 2 we get, next is this, I'll writing it here, 1 upon s into sine theta, this entire bracket, negative sign I'm shifting there on the right hand side, so it is d by d theta into bracket sine theta multiplied by ds upon d theta, this first term, plus 1 upon t sine square theta into d square capital T upon d phi square is equal to minus lambda. So this right hand side, I have shifted this negative sign on the right hand side, and that gives me this. So now look at here, to separate, here I am getting this sine square theta inside this term 2. Now to remove this sine square theta, what I have to do, I have to multiply each and every term by sine square theta. So throughout this equation, and that gives me sine theta upon capital S into d by d theta of sine theta into ds upon d theta, this first term, plus 1 upon t only, this sine square theta will get cancelled, into d square capital T upon d phi square is equal to minus lambda into sine square theta, because I am multiplying each term of this above equation by sine square theta, and therefore this gives me this. So here also shown in this equation, this part, second term, is completely independent of the theta, so it is only dependent upon phi. So I can rewrite this 1 upon t into d square capital T upon d phi square is equal to, minus sign is there, I can take this term, it will become minus, so minus outside of this, and then sine theta upon capital S into d by d theta of sine theta into ds upon d theta, this is my first term, and minus, now it becomes plus lambda times sine square theta. Now look at this equation again, I can call this to be equation number 4. For equation 4, left hand side is function of phi only, whereas right hand side is function of theta only. So again we can use the same mathematical treatment here, that this equation or equation true will be, the 4 will be true only when left hand side of this equation is equal to some numerical constant, as well as right hand side of this is equal to some numerical constant, and this time we are selecting this numerical constant to be minus m square. Now you will say that how to select a constant, whether in the earlier we have selected it to be lambda, now I am selecting it to be minus m square. So that is what the physician's approach, that is what the physician's intuition, that is what the, depending upon the symmetry of the problem, this type of constants we have to choose. So in this case we have to choose this constant to be m square. So we'll write once again, the equation 4 will be true only when both LHS and RHS, now we have to write this type of statement several times, at least twice in each such derivation, LHS and RHS are equal to some numerical constant, and this time we are taking, say, minus m square. Now this is my constant. Okay, so when we actually go for the series solution method, at that time we'll come across why we are putting this constant this way. So rewriting, and therefore separating from this equation 4, I'll get first 1 upon t into d square T upon d phi square is equal to minus m square. So rearrange this again, t can be taken on that side, so it becomes and again this m square can be taken on the left hand side, so it becomes d square T upon d phi square plus m square into capital T is equal to 0. This is my equation 5. So this is 5-part equation. Okay, equation 3 was r-part equation, equation 5 was 5-part equation, so 2 of them has been separated here. So I can make this to identify, this is my separated equation. So in bracket I have written this way. Now look at on this equation number 4, again on the right hand side. So that right hand side was minus, so my m square is again minus and minus, so you can remove this minus sign, and therefore next equation gives you sine theta upon capital S into d by d theta multiplied by sine theta into ds upon d theta plus lambda times sine square theta is equal to simply m square. Now you can put this case, so this equation is now depending upon, we have to rearrange this equation as further. So rearranging this what we will get is this so we have to remove this sine theta upon s, so we have to multiply each and every term by s upon sine theta. So here multiply capital S upon sine theta, we get multiply our equation by capital S upon sine theta. So what we will get is this S upon sine theta, you will get, sorry, S upon sine square theta, not sine theta, sine square theta. So one of the sine theta gets cancelled, S also get cancelled, so we get 1 upon sine theta into d by d theta of sine theta into ds upon d theta as it is. Then sine square theta and this lambda is there, so sine square theta is there, I am multiplying it by s upon sine square theta, so it becomes simply plus lambda into s. Sine square theta gets cancelled, is equal to m square into s upon sine square theta. Right hand side is also this. So take this term on the left hand side and you will get next term is 1 upon sine theta into d by d theta of sine theta multiplied by ds upon d theta, entire bracket here, and plus I can take lambda minus, so this term is taken here, lambda minus m square upon sine square theta bracket, and this time s is equal to 0. This is my equation. So you see the number of this equation, this is equation number 6, equation number 6. So this is your theta part, s part equation, s part equation, and that is how we have received or we have obtained. This is r part equation, equation number 3, equation number 5 is phi part equation, and equation number 6 is the s part equation. That is how we have separated 3 equations. Okay, that is the number of parameters in this case in spherical polar coordinate system are 3. So I am getting 3 separate equations which are to be solved further. These are ordinary differential equations we obtained, and in the process we have written 2 constant. One is lambda and second is minus m square. So n is equal to 3, so n minus 1, that is 2 constants are there. That is what shown here. So we can rewrite in short thus: by separating variables in Laplace equation for spherical polar coordinate system, spherical polar coordinate system, I got this. These are, we write in short all these equations. So first one is d square r upon small dr square plus 2 upon r into d capital R upon small dr minus lambda upon r square into capital R is equal to 0. As I said, this is r part equation, r part equation. Then second equation I got theta part equation is 1 upon sine theta into d by d theta of sine theta multiplied by ds upon d theta. This is first term, and plus second term is lambda minus m square upon sine square theta into capital S is equal to 0. This is called as S part equation. This is S part equation. And finally the simple one is d square capital T upon d phi square plus m square into capital T is equal to 0. This is called as phi part solution or equation. This is how we got 3 variables separated, 3 different types of differential equations we have obtained from Laplace equation in the spherical polar coordinates. And in the process we got 3 independent differential equations, ordinary differential equations, and 2 constants, that is first constant is lambda and second constant we have just now written it is minus m square. So I got two constants and three differential equations. Likewise, the same method is to be applied for all other. Now for example, when we go for Laplace equation in the cylindrical coordinate system, again we have to follow the same treatment. That is and also we are going to get three ordinary differential equations when we separate all these variables in the cylindrical coordinate system, as well as there also we have to put two numerical constant as per our choice or as per symmetry involved in this particular physical problem. So here we have finished this first article, that is the separation of variable of Laplace equation in the spherical polar coordinate system. So thank you all for patiently listening this.